So today I will talk about our DREENA framework, which is based on dynamical energy loss formalism, and how we can use this framework to explore QGP properties with rare high PT light and heavy flavor particles. And this work is done in collaboration with Dušan Žigić, Stefan Stojko, Bojana Blagojević, Jussi Ovinen, Igor Salom, Marko Đorđević, and Pasi Huvinen. So, as we all know, the energy loss of high PT particles traversing QCD medium is considered to be an excellent probe of QGP properties. And theoretical predictions can be generated and compared with the wide range of experimental data coming from different experiments, collision systems, collision energies, centralities, observables. And then this comprehensive comparison of theoretical predictions and high PT data can be used together with low PT theory and data to study the properties of creating QCD medium, that is for precision QGP tomography. However, to be able to implement this goal or this idea, it is crucial to have a reliable high PT parton energy loss model. And with this goal in mind, over past several years, we developed dynamical energy loss formalism, which I will outline in the next few slides. So, however, before going and discussing dynamical energy loss formalism, I will first give here the brief outline of the talk. So, I will first discuss the dynamical energy loss formalism in quark-gluon plasma, and then our development of fully optimized DREENA framework, which allows, in which this dynamical energy loss formalism is implemented. And then this goal of development of this DREENA framework was to allow systematic comparison of experimental data and theoretical predictions obtained by the same formalism and the same parameter set. In particular, we want to develop a framework which can systematically generate predictions for different high PT observables, such as RA and V2, different collision systems, lead, xenon, and other small systems, then different probes, both light and heavy, different collision energies, different centralities, and so on. Within this, our main goal is to introduce full medium evolution in the model, where we first start with 1 + 1D Bjorken expansion, and then we continue to 3 + 1D medium evolution, which will be also presented today. Within this, then we will discuss one important question, and that is how to differentiate between different energy loss model. In particular, what is an appropriate observable and what are appropriate systems to assess the energy loss path length dependence. And finally, I will discuss how we can use DREENA framework to infer the QGP properties, in particular, in this case, to infer QGP thermalization time from the data. If I'm going too fast, please let me know. So, just a moment. I don't know, something blocked. Okay, so I will first concentrate on the energy loss in quark-gluon plasma and our development of the dynamical energy loss formalism. So in general, there are two types of energy loss losses in quark-gluon plasma. So first one is radiative energy loss, and the second one is collisional energy loss. And in most simple way to distinguish them, we can say that radiative energy losses come from the processes in which there are more outgoing than incoming particles. That is, as a outcome of the radiative energy loss, additional radiation of gluons occurs. On the other hand, in collisional energy loss, these are the processes in which there are the same number of incoming and outgoing particles. That is, the energy and momentum is exchanged between already existing particles. So, for a long time, it was considered that collisional energy loss is negligible compared to radiative, and that is that the radiative energy loss shown here is generally dominant energy loss mechanism in quark-gluon plasma. However, this led to a well-known heavy flavor puzzle at RIC, which I will present here. So here are shown non-photonic single electrons RAA for them as a function of momentum, and here are shown predictions which are obtained by radiative energy loss only. And by looking at these predictions and compare them with the data, we see an obvious disagreement between the theory and the data. And this led to a conclusion that radiative energy loss alone is not able to explain the single electron puzzle as long as realistic parameter values are taken into account. So then this leads to a question, does the radiative energy loss really controls the energy loss in quark-gluon plasma, or there are some other energy loss mechanisms that are also important, but they are not included in the energy loss models? And the first logical question was, is collisional energy loss also important? And to address this question, we calculated collisional energy loss in a finite-size QCD medium. To do this, we consider a medium of finite size L, which is in thermal equilibrium at temperature T. And this is the main order collisional energy loss diagram that we had to calculate. It shows a particle which is produced inside the medium, which travels, for example, to the right. And then at some distance, which is smaller than the size of the medium, it interacts with one parton in the medium and exchanges one gluon. So this gluon is exchanged in the medium, so it has to be described by the effective medium modified gluon propagator, shown here, because the medium has finite temperature, and so this is medium modified gluon propagator. So I will not go into the analytical details of calculations, which are presented in the paper shown here, but I will show the results. So here, a comparison of collisional and medium-induced radiative energy loss for charm and bottom quarks. Here for as a function of momentum for fixed length of the medium, and here for as a function of length of the medium for fixed momentum. And by looking at these two figures, so collisional energy loss corresponds to full curves, while dot dashed curves corresponds to radiative energy loss. And by looking at these figures, we clearly see that collisional and radiative energy losses are comparable. And in some cases, for example, for bottom quarks, the collisional energy loss can even become larger than the radiative energy loss. So then this leads to a conclusion that collisional energy loss is important, and it has to be included in the calculations of jet suppression. So here are single electron predictions, which are obtained by including both collisional and radiative energy losses. And by looking at this figure, we see that we have an obviously better agreement than previously with the data, but the agreement is still not good enough. However, this inclusion of the collisional energy loss led to a fundamental problem with all existing radiative energy loss calculations. And the problem is that up to that time, all radiative energy loss calculations were based on static QCD medium approximation, which are modeled by Okawa potential. And the problem is that with such approximation, collisional energy loss has to be exactly equal to 0, because there is no recoil. So there is no collisional exchange of possibility for the collisional energy loss. However, as I showed on the previous slide, collisional and radiative energy loss are shown to be comparable. So this leads to a conclusion that introducing collisional energy loss is necessary, but on the other hand, it is inconsistent with the static approximation. And then this leads to a second conclusion that static QCD medium approximation should not be used in the calculation of radiative energy loss calculations, and that dynamical QCD medium effects have to be included. So with this goal in mind, we wanted to compute the both light and heavy quark radiative energy loss in dynamical QCD medium of thermally distributed massless quarks and gluons. And the reason behind our goal was there were two reasons. First, to address the applicability of static approximations in radiative energy loss calculations. And secondly, to compute collisional and radiative energy losses within a consistent theoretical framework. So to do this, what we wanted to do is to compute the medium-induced radiative energy loss for both light and heavy quarks to a first that is lowest order in number of scattering centers. For this, we consider the radiation of one gluon, which is induced by collisional interaction with one parton in the medium. In distinction to the static UCD medium, we now assume that this interaction with this parton in the medium, that this parton is moving, that is dynamical particle. So this is why this is called dynamical energy loss. And to calculate this energy loss, we consider a medium of finite size L and assume that the medium has finite temperature T and that this collisional interaction has to occur inside the medium. So the calculations were performed using two-hard thermal loop approach. And here is the typical diagram that we have to compute. So this diagram shows a particle which is produced at T equals 0 and then travels to the right. And then at some distance L, which is smaller than the size of the medium, it interacts with one parton in the medium and then radiates one gluon. So since this radiated gluon is a realistic particle, its energy has to be larger than its momentum. On the other hand, for this exchanged gluon, it can be shown from the conservation of energy and momentum that its energy has to be smaller than its momentum. So to calculate the square of this diagram, we can use optical theorem, which reduces to calculating two imaginary parts of this diagram. So this dashed line shows which propagators have to be cut. And when we cut these propagators, for this radiated gluon, we take quasi-particle contribution, that is from the cut hard thermal loop propagator, that is contribution in which energy is larger than its momentum. And for this exchange gluon, we take Landau damping contribution, or the contribution in which the energy is smaller than momentum. So this is one technical slide, the only one which is technical slide in this talk, and it shows.
Sorry, Magdalena, can I ask a question?
Yeah.
On the previous slide, maybe you're going to cover that in this slide, but you said you had Landau damping, but that is there a Debye mass that goes into that
No.
based on the quark mass?
I think I will now explain what it is. The Debye mass goes into radiated. The Debye mass goes into this radiated gluon. That is to this quasi-particle contribution. Right. It does not go. It indirectly goes here, but it is not directly there. So it is not exactly that. So I will try to explain this, and if you have again question, we can discuss.
Okay.
So this is one hard thermal loop gluon propagator. And then cut one hard thermal loop gluon propagator is shown here. And then this rho T and rho L are transverse and longitudinal spectral functions. And these transverse and longitudinal spectral functions have the following form. So this form has this delta function of L squared minus self-energy, and self-energy is larger than 0. So from here, it follows that the energy has to be larger than its momentum. And this is this quasi-particle contribution that corresponds to radiative gluon. On the other hand, for this exchanged particle, there is this part which corresponds to this theta function, in which we see that energy is smaller than momentum. So this is this virtual gluon, or so-called Landau damping contribution, or exchange gluon contribution. So for this radiated gluon, we have shown in this paper that though there are two contributions, both longitudinal and transverse, that longitudinal can be neglected, and then the transverse contribution can be simplified to a very simple form, which is shown here, where this omega is momentum plus mg squared, such as gluon gains mass, where mass is Debye mass divided by square root of 2. So basically, this complicated relation reduces for radiated gluon as this medium contribution as if gluon has a mass due to this finite temperature QCD medium. On the other hand, for this virtual exchange gluon, cut one hard thermal loop gluon propagator cannot be further simplified, since both these transverse and longitudinal contributions are important, and these are quite complicated functions. I don't have them in this slide, but you can find them anywhere in any hard thermal loop book. So they're quite complicated, and all of them have to be kept in the calculations. Okay, does this answer your question?
Yeah, I think I understand where it goes in now.
Okay, okay. So, moreover, there is more than one cut of the Feynman diagram that can contribute to this energy loss in finite-size QCD medium. So, just a moment. Okay. So we see here that that this is this central cut. So for this diagram, there is this central cut. But then also it can happen, and it corresponds to this, where this particle is initially on shell. But this initial parton, since it is produced in the medium, can be also off shell. And then in that cases, you can have contributions from asymmetric cuts, this left cut and the right cut. So all these contributions have to be taken into account. And these terms interfere with each other, leading to the nonlinear dependence of the jet energy loss, and that is to the appearance of the LPM effect in high energy jets after all contributions are taken into account. So what we did is we calculated all the relevant diagrams that contribute to this energy loss along the lines that I explained in the previous slide. So it should be noted that each individual diagram is infrared divergent due to the absence of magnetic screening. But what is very interesting is that this divergence is naturally regulated when all the diagrams are taken into account. So therefore, this calculation is highly non-trivial, since all 24 diagrams have to be included to obtain a sensible result. And we finally obtain an explicit analytical expression for the energy loss in dynamical QCD medium, which is presented by the equation shown here. So in the previous several slides, I showed the motivation for introducing the basis of dynamical energy loss, formalism, and I will not go more into the details about this formalism, but over the past several years, we further developed the state-of-the-art this energy loss formalism, which has several unique features in the description of high-PT parton-medium interactions. So as I already mentioned, it includes finite-size, finite-temperature QCD medium of dynamical that is moving particles. It is based on finite-temperature field theory and generalized hard thermal loop approach. It has the same theoretical framework for both radiative and collisional energy losses. It is applicable to both light and heavy flavor. In this formalism, the divergences are naturally regulated. Then the finite magnetic mass effects were also included, running coupling is included, and most recently we also relaxed the soft-ground approximation. So this is a complex model which has many ingredients, and in this paper we systematically investigated how important are these ingredients and showed that all of them are necessary to accurately explain the data. And finally, to generate predictions for high-PT observables, we developed DREENA framework, where DREENA stands for Dynamical, Radiative, and Elastic Energy Loss Approach, which is a fully optimized computational numerical procedure in which our dynamical energy loss is implemented. So we here show predictions for DREENA B framework, where B indicates Bjorken 1D evolution, Bjorken expansion, and the model up to now provided a good joint agreement with a wide range of RAA and V2 data for different probes, for different collision energies, for different centralities. And this comprehensive agreement was obtained by using the same numerical procedure, the same parameter set, and with no fitting parameters used in model testing. Then we have also managed to resolve the long-standing heavy flavor puzzles at both RIC and LHC. And we have also shown that our model has a clear predictive power. That is, in 2005, we predicted that RAA for both light and heavy flavor at 2.76, which is shown in dashed, and 5T, which is shown with full curves, will be the same. And this was due to an interplay between the rising the temperature and decreasing in the steepness of the PT distributions. And then this was actually confirmed in 2006 by the experimental data. So we moreover here present our most recent development, which are our results obtained by 3+1D hydro DREENA framework, which is this 3+1D is implemented into our DREENA framework. And contrary to all available models, we see a very good agreement for both RAA and V2 data, which are moreover obtained with no fitting parameters. And contrary to all other available models, we see that it appears that there is no V2 puzzle within our model. So from this, we can conclude that contrary to widely accepted paradigm of dominant importance of proper medium evolution description, our results strongly suggest that for high PT data, actually proper description of parton-medium interactions is much more important than the medium evolution.
Can I ask a question here, Magdalena?
Yes.
So how is the centrality evolution taken into account? Do you have temperature variation or some kind of
so what we did,
average scattering or something like that?
3+1D was run by using the model, which is it is called the model developed by Niemi, Pasi, and so on, and it is so-called age model. So I don't know how they calculate the centrality. As far as I understand, they use some fixed B for the centrality. Though now we are moving to event by event, and then we will really do have centrality regions equivalently to the experiment. And
right. So
and then you obtain a temperature profile, and whatever temperature profile we obtain, we simply plug into our DREENA framework, and then we calculate what is the suppression and what is the V2.
So it's Glauber temperature, basically.
Glauber, yes, Glauber initial conditions, yes. In this case, it is Glauber initial conditions, yeah. Okay.
So maybe another question, Magdalena. Yes. So when you're treating the radiative energy losses, have you somehow included the dead cone effect or not?
Yes.
It's inherent in your probe.
Okay, I can show you exactly. So the dead cone effect is not that simple. So you can see this slide. And you, unfortunately, I didn't write what is this Xi factor. But this Xi factor is the mass of the heavy particle plus the mass of the gluon. Mass of the heavy particle times x squared plus mass of the gluon. And x squared is omega. Omega is the energy of the radiative gluon divided by the initial energy of the jet. So here the dead cone is included in this expression here. So it is included here, it is included here, it is included in this part, it is included in this part, and in this part. So it is everywhere it is included, but the expression is not as simple as you would say from initial study by Karzev and Dokshizer. So it is much more complicated expression. But that is the main advantage of our approach, that this approach is applicable to both light and heavy flavors. So for light, we put the bi-mass for the light flavor, that is the bi-mass divided by square root of 6. On the other hand, for heavy flavor, you use for Chan 1.2 GeV mass. For bottom quark, we use 4.75 and so on.
Okay, thank you.
So it is included.
Yeah, good.
Sorry,
Yes?
one more question. So this is sort of where I originally asked about the Dubai mass, right? Because I was looking at recently, there's this work from the Jetscape people where they do the heavy flavor. They basically write a modified splitting function that where they put this mass, and it appears sort of similar to this. You have 1/1 plus sort of mass squared in this units that you have here. So is it reasonable to expect that the larger the mass, if I kind of translate it to a physical, the device screening would be smaller? It's sort of balancing itself out?
No. Debye mass does not have anything to do with the mass of the quark, of the jet. These are two completely separated things. So you see, the Debye mass is shown here.
That's a mu squared.
Yes, and here, if you have a gluon, then you will also, since gluon has a mass, then you will also have a contribution from the Debye mass, and it is going to be here. So it is not to be that trivially simple, but it does not modify the mass of the heavy flavor itself. You know, the heavy flavor is 1.2 GeV or 4.76. The Debye mass is relatively small. The mass appears here as m squared. So if you put m squared of 1.2 squared, and then you put the Debye mass divided by square root of 6, and then you square it, it is going to be negligible compared to this. So this is not going to interfere.
Okay. No, cool. Thanks.
Okay. Okay. So then I come to this slide, I guess. So now I come to the second part of my talk, where we want to address how we can differentiate between different energy loss models. So with regard to this, know that path length dependence provides an excellent signature for differentiating between different energy loss models, and consistently also between the underlying energy loss mechanisms. For example, some energy loss models have linear path length dependence. So for example, collisional energy loss. Some have quadratic radiative energy loss in its subsymptotic limit, for example. And then the dynamical energy loss path length dependence is somewhere between linear and quadratic due to both collisional and radiative energy loss models included in this model. So the question is, how can we infer this path length dependence? And to do this, to address this question, we first ask what is an appropriate system for this study. And with regard to this, we argue that comparison of suppressions in lead-lead and smaller systems, for example, recently not measured xenon-xenon, is an excellent way to study the path length dependence. The reason behind this is the following. From the suppression calculation perspective, almost all properties between these two systems basically remain the same. They have the same initial momentum distribution. They have, we can show it, they have the same average temperature for each centrality region, and they have the same path length distributions up to rescaling factor A to the 1/3. That is the main property differentiating these two systems is its size, that is this rescaling factor A to the 1/3, which therefore makes comparison of suppression in lead-lead and xenon-xenon as an excellent way to study the path length dependence. So the second question is, what is an appropriate observable? And with regard to this, the ratio of two RAAs seems as a natural choice, and this was proposed before. However, in this way, we can show this. So in this way, the path length dependence cannot be naturally extracted, as shown in this slide. So we here plotted RAA in xenon-xenon divided by RAA in lead-lead, and we as a function of momentum for 3 centrality regions, 0 to 5, 20 to 30, and 50 to 60. And by looking at these figures, we see that this ratio approaches 1 for high centralities and high momentum, which could lead to a conclusion that there is no path length dependence if this is 1, but on the other hand, we know that the energy loss has a strong path length dependence. Also, we see that this ratio strongly depends on the centrality. The larger the centrality, the lower this ratio. So from this, we see that this that from this figure and from this observable, no useful information cannot be deduced. And we can ask what is the reason behind this. And to do this, we use the scaling arguments that fractional energy loss is proportional to T to the A and L to the B, where A is scaling factor for the temperature and B is scaling factor for the length. We have shown that this is approximately okay. And then when we use this, we can calculate the ratio of RAA in xenon, and lead, and we obtain the following expression shown here. And by looking at this expression, we see that this is quite a complicated relationship, which depends on the energy of the jet, which is hidden in this factor C. Then it depends on the temperature on the medium, it depends on the length, it depends on the centrality, and so moreover, as a conclusion, we see that this is a complicated relationship from which we cannot extract the path length dependence. However, based on this study, we propose to use the ratio of 1 minus RAA instead. And if we do this, we obtain the following thing. So we see that we have a simple dependence, which depends only on the size of the medium, this A to the 1/3 ratio, and the path length dependence, this is this exponent B. And then if we now plot this ratio, so it is plotted here, so this is this 1 minus RAA ratio for xenon, and lead, for two centrality regions as a function of PT. So one centrality is 30 to 40 and another one is 50 to 60. And moreover, so we here plot this for light flavor, this is this red curve full. Then for D mesons, this is this blue dashed curve. And for B mesons, this is this green dot dashed curve. We see that this path length dependence is, can be extracted in a simple way, and there is no significant, almost no centrality dependence when we go from one centrality to another one. So from this, we conclude that 1 minus RAA therefore seems as a natural observable, which we can call path length sensitive suppression ratio. So then we can ask, yes?
Back to the previous slide. So is there a reason for why wouldn't you look at the most central to see?
Okay, I can, because this, you see this? So in order to use this simple relationship, we need to have a small energy loss. So all this analytical derivation is applicable when the energy loss is small. And to use this analytical derivation, we need small energy loss, and small energy loss is applicable when you have high PT and when you have higher centrality. So you have to have both. So basically, we will see that you cannot apply this in this region because the energy loss is going to be large, and simply this relationship will not work. But if you are at high centralities and high momentum, then this relationship will work, and that is why we advocate using this region.
So that has nothing to do with perhaps having a different energy density or temperature. I know you're going to talk about. You're going to talk about temperature? No, you assume that.
This will only extract the path length dependence. So basically, in this way, if you go to high centralities and high momentum, you can really, as I will demonstrate on the next slide, you can really extract the path length dependence very nicely by using this observable. It is independent of anything else, on the temperature, on simply, that is our proposal, and it remains to be tested by high luminosity experiments, but we believe that that this observable is going to be independent on the temperature, density, and so on. It will only depend on the path length dependence. Right. And I will demonstrate on the next slide to try to persuade you that this is really the case.
Okay, well, that's one of your assumptions initially, right? That the temperature doesn't change, right?
Actually, so the average, we calculated that the temperature should not change. This is not our assumption. This comes from our calculation that the average temperature will not change.
Okay.
We believe that it is going to be correct, but as I said, this is our calculation. If it turns to be right, that's fine. If not, that is what we did, what we calculated.
But that's all. I'm just
Go
trying
back to the paper and to discuss how this is calculated. I can.
Okay. Go ahead. Thanks.
Yeah. So I now ask, what about smaller systems? Because as we all know, there is precision measurements for smaller systems are proposed for krypton, argon, and oxygen, and we hope that we will become available in the future beam size scan at the LHC. And the question is, can this system be also used to extract the path length dependence for the of the energy loss? And to do this, we here calculate, we just concentrate on the charge hadrons because we have shown that we will obtain the equivalent results for both light, for heavy flavor, but in general, heavy flavor is going to be harder to measure. So this is, for this particular goal, light flavor is going to be more suitable because it is going to be more abundant. And then we here plot this 1 minus RA ratio as a function of momentum for 4 different systems: xenon lead, krypton lead, argon lead, and oxygen lead. And then what we see from here is that if you look at these figures, we see that this 1 minus RAA is almost independent on the centrality for, I just forgot to say that these 3 figures correspond to 3 different centrality regions. I don't remember which one is exactly, but one is 30 to 40, 40 to 50, and 50 to 60. So we see that this ratio is almost independent on the centrality region. Then secondly, for all 4 systems, this 1 minus RA ratio shows the same behavior. That is, it is very robust with respect to extracting path length dependence. That is, these figures are almost the same for these 4 systems. Then it reliably recovers collisional and radiative energy loss path length dependence. To discuss this, let's discuss these figures. So this figure, if we take our full energy loss formalism, which includes both radiative and collisional energy loss. Then we also plotted 2 scenarios. This scenario corresponds what would be the path length dependency if we take into account only collisional energy loss. And this scenario corresponds to what would be the path length, extracted path length dependency if we use only radiative energy loss. And by looking at this figure, we all know that collisional energy loss has linear path length dependence. And exactly, we see that this is exactly recovered, linear path length dependence. On the other hand, radiative energy loss asymptotically approaches quadratic path length dependence, and we really see that with this, we recover this radiative energy loss limit. So we see that our proposed observable reliably recovers collisional and radiative energy loss path length dependencies for all 4 systems. And from experimental perspective, smaller systems might be more convenient for applying this observable, as the region of applicability between L and L square increases with decreasing the system size. So here it is going to be, this difference is going to be around 0.1, which is relatively smallish. And here it is almost 0.3, so it is going to be relatively large. So consequently, we propose that this 1 minus RA ratio is simple, robust, and reliable observable for extracting the path length of the energy loss. So before going to the last part of the talk, I will give a summary up to now. So we introduced DREENA framework, where DREENA is a computational implementation of the dynamical energy loss formalism. Then, contrary to other available approaches, with this framework, we obtain a very good agreement with both RA and V2, even with full 3+1 dehydroevolution implementation. And this suggests that for high PT data, accurate description of high PT parton-medium interactions is much more important than accurate description of medium evolution. Then, based on numerical calculations and simple analytical derivations, we propose a new observable, which we call path length sensitive separation ratio. And we show that the energy loss through this observable, the energy loss path length dependence can be extracted in a simple, robust, and reliable way. And we expect that the beam size scan, future beam size scans at the LHC will provide an excellent opportunity to assess this path length dependence. As an outlook, we consequently expect that dynamical energy loss formalism can provide a basis for the state-of-the-art QGP tomography tool that is to jointly constrain the medium properties from the point of both high and low PT data. And with this outlook in mind, I come to the last part of my talk, which presents the first step in this direction. And this is the goal of inferring the bulk UGP properties from high PT theory and data. So, as we all know, bulk UGP properties are traditionally explored by low PT observables that describe collective motion of 99.9 particles % of QCD matter, while on the other hand, rare high energy probes are almost exclusively used to understand high PT parton-medium interactions. On the other hand, while high PT physics had a decisive role in the description in the QGP discovery, it has consequently it was rarely used to understand bulk QGP medium properties. But on the other hand, some important bulk QGP properties are known to be difficult to constrain by low PT observables and corresponding theory and simulations. So consequently, we here advocate so-called high PT QGP tomography, where bulk QGP parameters are jointly constrained by both low and high PT physics. That is, we will demonstrate how the analysis of one of these separate regimes can be useful for the description of another, and for the first time constrain the description of the bulk by the analysis of high probes. So the main idea behind this QGP tomography is the following. To put it simply, when high energy particles go through medium, they will lose energy. And this energy loss will depend on the properties of QGP medium. That is, if you have different temperature profiles, different evolution of the system, you will have different energy loss. What is now very important is that we can realistically predict this energy loss, and then consequently these high PT probes become powerful tomographic tool, and we can use them to infer some of the bulk UGP medium properties. And one of these properties in particular that we want to analyze is the QGP thermalization time. And we now discuss how we can use high PT RA and V2 to extract or to further constrain the QGP thermalization time. So the dynamics before thermalization and applicability of hydrodynamics and therefore the associated energy loss phenomena are not established yet. So to avoid speculation and to provide a baseline calculation for further studies, we assume free streaming of high PT particles before thermalization and neglect the pre-equilibrium evolution of the medium. Then after thermalization, the QCD medium is described as relativistic viscous 3+1 dehydrodynamics, and high PT probes start to lose energy through medium interactions. Consequently, the thermalization time is an important parameter which is important for the evolution of the system and interactions of high PT particles with the medium.
So Magdalena,
yes?
Just to be clear on the language, if you go back one slide.
Yes.
You use particles in two different senses, right? So the rightmost box, you mean partons, right?
Right, Mog. This box?
Yeah.
Yeah, I mean high PT particles.
But that.
No, for high PT particles, we assume free streaming, and for low PT particles, we assume no pre-equilibrium interactions.
Right, but this is all pre-equilibrium before thermalization, right?
Yes,
but it's
yes,
not
before
really.
Yes.
When you say particles, because there's students here too, you mean quarks and gluons, right?
Yes, of course, of course.
Okay.
Sorry.
Later, you say particles, meaning those that are observed, right?
Yes. Okay, I will make sure that I.
Yeah. Thank you.
Thank you. So, the study by Bass et al. Showed that comparison of, that is a full-fledged, we all know about this, that is full-fledged study by Bass et al. In which they showed that comparison of relativistic hydrodynamics with low PT data is insensitive to a wide range of thermalization time. That is, the thermalization time can be anything between 0.2 and 1.2 Fermis. They have the same assumption of free streaming of after thermalization and no interaction before thermalization. So this conclusion was independently confirmed by our systematic analysis. That is, we here use 3+1D viscous hydrodynamics and run with 6 different thermalization times: 0.2 Fermis, 0.4 Fermis, 0.6, 0.8, 1, and 1.2, and compare them with Alice data with particle spectra for Alice data. And we see good agreement with low PT data, confirming this low sensitivity, which is already observed by a separate study. So then we ask a question: can this indeterminacy be further constrained through high PT theory and data? And to do this, we used our most recently developed DREENA A framework, where A stands for adaptive, meaning that this framework is fully modular, and that means that in this framework we can incorporate any temperature profile that we obtain. In this case, we included these 6 temperature profiles, which we obtained from 3+1D hydro, obtained for 6 different thermalization times. And then we generated RAA predictions for high PT, for RAA, and for V2. And then these predictions are shown for these 6 different thermalization times. And by looking at these figures, we see that high PT predictions can be clearly resolved against the experimental data, where low PT data show weak sensitivity. That is, they robustly prefer later tau nulla for both RAA and for V2. And moreover, we observe larger sensitivity for V2 predictions, where we see that our predictions asymptotically approach the high PT tail of the experimental data as tau 0 is increased. So then we also do this for heavy flavor, and then in this figure we show predictions for D mesons in full curves and B mesons with dashed curves, and we see that moreover this sensitivity is even larger for heavy flavor than for light flavor. Then we can ask, what is the reason behind such sensitivity? Or the second question, does jet quenching, can jet quenching start later than the thermalization? So a recent study by André et al. Proposed that jet quenching may start later than the thermalization of bulk UCD medium, which may strongly impact high PT V2 predictions and explain the V2 puzzle. And to test this, we assume the smallest thermalization time, 0.2 Fermis, and then generate T profile from this thermalization time, full 3+1D profile. Then we introduce different quenching times, 0.2, which coincides with this thermalization time, or 0.4, which is later, then quenching time 0.6, quenching time 0.08, or quenching time up to 1.2. So this quenching time 1.2 means that jets will start to interact with the medium 1 Fermi after the hydrodynamics starts. And then we test how these predictions will look like for RAA and V2 by using this later quenching time. And by looking at this, we see that RAA is weakly sensitive to changing this thermalization time, but on the other hand, V2 is surprisingly entirely insensitive to these different quenching times, and consequently does not support this idea of this proposal that jet quenching can start later than thermalization. So it clearly disputes this idea that these two can be separated, which on the other hand is quite reasonable, because this is relatively non-intuitive idea, because there is not really a reason why would quenching start later than the bulk medium interactions. Why would high PT particles start to interact with the medium later than 99% of other particles start to interact with each other? So this idea is disputed. So if this is not the reason behind such...
Before you move on, Magdalena?
Yes?
Is there an intuitive reason why the V2 doesn't change? I would have thought changing, I mean, if I think of high PT V2 as being a path length difference, shouldn't that have an effect depending on what time it starts to interact?
I will try to answer this question in 2 slides. So,
okay.
And if yes, it is not that easy to see it, but there is a reason, and I will try to explain it in 2 slides.
Okay.
So, okay.
Yeah, sorry. Before we move on, just a quick question. Maybe you will also talk about this later, but is there a reason, like, why there's like this big jump between 2 and 5 GeV on the V2? Like, I'm trying to understand what this plot is trying to convey on the right.
3 and 2 and 5 GeV.
Yeah, so basically, if you look at the V2 plot, between 2 and 5 GeV, there's no...
Okay, I forgot to say that. So we wanted to put on the same footing, so this is logarithmic scale, and we wanted to put on the same footing how low PT agreement look like, how from our full hydro we obtain our agreement is with low PT for these different times, and then how it looks for high PT. That is very important question, but let me go back 1 slide before. So look at this. So here we have this low PT region, and for this low PT region, we show our agreement with V2 data that is obtained with our 3+1D hydro applied to low PT region. And we see that all these 6 scenarios with 6 different thermalization times almost exactly overlap with each other. So this shows that indeed low PT is insensitive to these different thermalization times. On the other hand, high PT observables show a clear separation between different scenarios. So this, thank you for asking this question. This really shows that where low PT is insensitive, high PT shows large sensitivity. And this is the reason why we propose this high PT QGP tomography. That is why we say we have to use both low PT and high PT to constrain the properties of QGP plasma. That is where low PT are insensitive. We can first start to use low PT and try to constrain the parameters as much as possible to low PT. But then once we do that, let's then use high PT to constrain them further, and this demonstrate exactly that once low PT starts to be insensitive, high PT can be used to discriminate between different scenarios. So this is why we plotted them on the same plot, because logarithmic scale enabled us to do this, to show both of them, both low PT region and high PT region at the same plot. Okay, does this answer the question?
Yes, thank you. So just a follow up, do we have any model for the intermediate PT region?
For the intermediate, no, we don't do this. So basically in our group, we have 2 persons who are working on hydro. This is Pasi Huvinen and Jussi Auvinen. And they are working on 3+1D hydro. They also implement other hydro models. We really have a nice idea to test many different temperature profiles and so on. And this is ongoing idea. And then on the other hand, our group is concentrating on high PT. So basically, these are the regions that we cover. We have specialists in this region and we have specialists in this region. We don't work in this intermediate region. We don't have a model for that.
Okay, thank you.
Okay.
So Magdalena, that's very nice. I mean, your previous slide, and it's rather intuitive, which is also nice. That the high PT observables are sensitive to early times, and the low PT observables take time to evolve. That's nice. Thank you.
Yes, thank you. This really turned out to be more than we expected. We were worried that the temperature profiles are so similar that it will not give a large difference, but it turns out that they are different and that they really make a difference in high PT where they don't make a difference in low PT. So I will discuss just continue to the next slides. So the second question, since this later quenching time is not the reason behind this sensitivity, we ask whether this sensitivity is a consequence of the differences in the temperature profiles. So to test this, we use 2 different centrality regions, 10 to 20 and 30 to 40, and then we concentrate to 2 different thermalization times, 0.2 and 1.2, so 2 extremes. And then we plot in-plane temperature profiles. For these 2, we compare in-plane and out-of-plane temperature profiles, which are averaged over all sample jet paths. And in-plane is shown with dashed curves, and out-of-plane is shown in a full blue curves. So RAA is proportional to the difference in in-plane and out-of-plane suppression, in-plane and out-of-plane RAA. And the larger difference in in-plane and out-of-plane RAA is proportional to the temperature. The larger the temperature, the smaller the RAA. So this means that the larger the difference in the temperature profile, the larger the difference will be in the RAAs. So consequently, if we have larger difference in the temperature profiles, this will lead to larger V2. And what we see in these figures is, for example, if you compare this one and this one, you see that if you look at 0.2 Fermis, you have very similar to quite similar temperature profiles in in-plane and out-of-plane direction. On the other hand, if you go to 1.2 Fermis, these 2 temperature profiles are very different, and then this will lead to larger difference in in-plane and out-of-plane RAA, and consequently to larger V2. And then consequently, these differences in the temperature profiles are a major reason for such sensitivity. And to ask this previous question, which was why here everything is the same, what is happening, for example, let's concentrate on this temperature profile alone. This you cannot really see it, but if you put this on the top of each other, these are very similar. So if you fix this profile, and then if you move from 0.2 to 0.4 to 0.6 and so on, your RAA in plane and RAA out of plane will move in the same direction. So basically, once you subtract them, their average RAA is going to be the same, But on the other hand, their difference is going to again be the same. And once you cancel them, V2 remains the same. That is explained in one of our papers. It is not shown here, but you can look at the paper which is called about initial times. It was recently posted on the web in, I think, in January or February, and in that paper we really make a clear explanation why this happens and why we see that this is that this V2 is independent on the different quenching times. So it is not that easy to intuitively understand it, but it is really there. Analytically, it can be understood, but this is several lines of derivation to really see that. Okay.
Magdalena. So when you get the temperature profile here, this is not a gradient of the temperature in the medium. This is the profile of the temperature experienced by the jet as it travels, right? So this is like the local medium temperature relative to the jet. So once the jets traveled a certain distance, the medium is cooling off.
So that is the temperature. Okay, so we sampled all particles, many particles. I don't know, but it was several tens of thousand particles. And then for all of them, we took what temperature profile does these particles see, and then we average these temperature profiles for in-plane and out of plane, and we compare them. So we take particles, and then we say, let's say 10,000 particles going just in X direction, producing different points, and then just going in next direction. And what temperature profiles like that do they see? And then we average them. And then we say 10,000 particles go just in Y direction. And then if they go in Y direction, we sample all of these temperature profile, and then we average them. And then this is what is plotted on this figure.
Thank you. That makes sense.
Yeah, and then you really see that these temperature profiles, what jet sees is different in plane and out of plane if you use different thermalization times. It is simple as that.
Got it.
Okay, so I come now to my summary. So we here presented to our knowledge the first example where the parameter which is important for simulating bulk UGP evolution, but which is to a large extent is sensitive to the low PT physics, can be constrained by high PT theory and data. Specifically, we here used high PT RAN V2 to infer that late thermalization is clearly preferred by these experimental data. We have also shown that heavy flavors show larger sensitivity to thermalization time, which can be tested in the upcoming luminosity measurements. We have also shown that V2 is significantly more sensitive to tau 0 than RAA, where this sensitivity is due to differences in in-plane and out-of-plane temperature profiles. And finally, we conclude that this study hopefully demonstrate inherent interconnections between low and high PT physics, strongly supporting the utility of our proposed UGP tomography approach for extracting the bulk UGP properties by jointly studying and constraining these by both low and high PT data. And thank you for your attention.
Thank you, Magdalena. Yeah, so let's start with a few questions. So feel free to unmute your microphone and ask a question. I'll ask one if people are still thinking. So, yeah, I mean, the last part is really cool. I'm trying to like still wrap my head around it. So if you have a very early thermalization time, then that means that the temperature that you start, that the jet starts seeing is different than if you have a late thermalization time, right? Yes, yes. So this difference that you see in the high PT V2 is a consequence of that, right? I mean, it's like you're introducing the probe at different times. If you introduce it early, then it undergoes larger interaction versus later time. Is that right?
I would interpret it this way. If you use, if you introduce later thermalization times for hydro, then this hydro will generate different temperature profiles, and this temperature profile which is generated once you use 0.2 Fermis and 1.2 Fermis is going to be different. And the temperature profile which is generated once you use 0.2 Fermis is going to be such that that high PT particles will see that in plane and out of plane temperature profiles are almost the same. And this is, I think, the primary reason why there is so-called V2 puzzle, because most of the many models use, I think, Vishnu or music or something like that, hydro incorporate in their models, and then all of these models have very early thermalization incorporated in it, and then due to that you can never get high PTV2 with such a model. On the other hand, if you start your thermalization later, then simply the profile is such that it starts to separate in plane and out of plane, and then jet sees this, and this leads to larger V2.
Right. So for like, since you mentioned Vishnu, right? So like Vishnu gives you this sort of formation time. I think that's what you're also calling as thermalization time, right?
Yes.
Right. So okay, that totally makes sense. But there's no way in which we can like what I'm trying to think of is, if you have different initial condition, would that contribute to different thermalization time, or is thermalization time sort of a static property of the system?
So what we want to test that. So this is our future goal. At this point, we don't know what happens before thermalization. What we did is we tried to be very consistent with this study by Bass et al. They started with very simple scenario. They say no interactions before thermalization, free streaming for high PT particles before thermalization. So basically no interactions before thermalization. And then they tested to this large Bayesian approach, and with that they got that thermalization time is between 0.2 and 1.2. And then we said, let's do the same thing and see whether we can further constrain it to high PT data. First, we see that we really recover their results, and that what they obtained is really reasonable, really is recovered by our low PT studies. Moreover, we see this in this one, that V2 is completely independent on these different tau zeros, but we see that high PT is sensitive. So that is what we did. We can go then further and start to implement initial pre-equilibrium scenarios, and that is something that really both PASI and UC are thinking about doing it. But first, that is not that easy, though it is doable. And second thing, now we want to implement event by event. We want to test different, different parameters and so on. So simply, we don't have so much manpower to do that everything at the same time. So this is really our goal. So at this point, we really want many things to do, but this is the first thing that demonstrates that what we are proposing is reasonable.
It's very cool. Thanks.
Okay, thanks.
I have a question about, I think around slide 25.
Okay.
You say that this ratio of 1 minus REA might be better than just the ratio of the REAs.
Yes.
I think earlier this year, we, as Alice, we have the charged particle REAs, and we do have the ratio actually of so the ratio of the REAs, so not the 1 minus the REA. And it's on archive, but it shows that for lower PT, it is actually in central collisions for both of the systems. It shows to be compatible completely with Unity, and it doesn't seem to have this increase when you go to lower PT. I don't know if you saw this or what would be your take on that. Like there are still some large systematics, but if it turns out to be compatible with Unity, what would you conclude from that?
Well,
because then 1 minus would then also be the same. If the direct ratio is flat, then 1 minus will also be.
I really cannot say anything without seeing the results. I would have to see them. If you can send the link to me, and then I can see, and then maybe I can provide, like my opinion about it. But that discussing something that I really didn't see, then I'm really not sure.
Yeah, I don't know. We could go to the length of putting it on the screen, but I don't know if you.
Okay, that would be fine.
Maybe just for 1 minute then.
Should I remove myself from the screen?
Yeah, I think so. Yes, yeah, because you have such a huge number of slides. Maybe this is interesting. Let's see. So that will be this plot. You see the screen, right?
Yes.
Yeah, so here on the bottom is this ratio of the xenon over the lead.
Mm-hmm.
This is for central.
Okay.
And this is for 30 to 40 and 40 to 50%.
Mm-hmm.
And this is the ratio.
Yes.
And it seems to be relatively flat for low PT. Now, I don't know. So they took a similar D and charged the eta. So the centralities are somewhat different in both the systems, but the multiplicity is fixed.
Mm-hmm.
And then this is the case.
Okay. So first, what you did is you tried to compare the same. You change the centrality so that you can compare the same multiplicity. So this is not exactly the same. If you want to really divide them, you would have to look at both of them being 30 to 40 or both of them being 40 to 50. And secondly, our calculation is only applicable to high PT. So what we propose is only applicable at high PT, that is where energy loss is small, so that our analytical analysis can be applicable. Otherwise, we cannot deduce anything in the low momentum region because we cannot simply apply this relatively simple scaling. We cannot deduce anything analytically and get analytical understanding. We need to go somewhere where we can apply analytical understanding to understand it. And then we need to go to high PT region. And I would be interesting to see high PT region and the same centrality, and then I could discuss, but this is really not the same thing. So basically you in this case I would say that this is normal because you wanted to put the same charge particle multiplicity more or less to have the same system and to see whether these two are consistent with each other.
That's a very good point. Yeah. And would then the probe matter a lot since it's charged particles? Would it matter to do identified, or would then the jet REA be the best, or wouldn't it matter so much?
I think charged particles are perfectly fine because we would have to go to very high PT. And you would have to go to high centralities. And at high centralities and high PT, you don't have many particles. So it is the best to have as many particles as possible. So for that, it is the best to go with charge hadrons. And as I also said, just to try to share screen again, let me see. I guess this is it. Do you see it?
Yes.
I'm not sure whether. You see here the difference. If you look here, the difference between these two is 0.1 and here is 0.3. And if you want, with your error bars at high momentum and high centrality, if you go to high PT, you will have relatively large error bars, even at high luminosity. So because of that, it is best to have the particles which you have in abundance as much as possible so that your error bars are reduced. So I think charge handles are perfectly fine.
So CMS do have a result like that, right? Again, it's the ratio, not 1 minus ratio. So I've been trying to do the math in my head and failing, because I see that it at high PT is, I mean, the xenon-xenon to lead-lead at the same centrality is slightly greater than 1 at high PT. I don't quite know in which direction that would push the 1 minus.
Well, I don't know.
So I guess that was the thing, and I was trying to do that in my head, like, why does the 1 minus, why is that critical rather than just the ratio? I know you said, but it's sort of...
So here is the derivation. Unfortunately, I don't have a derivation, but never mind. RAA, if you go to this high PT, if I would have a pen and paper, maybe I don't have it. So maybe I can upload the paper and then show it. Never mind. So if you use, if you calculate RAA at high P, if you assume that delta E over E is T to the A and L to the B, and then if you assume that this delta E over E is very small, then RAA is 1 minus delta E over E up to the n minus 2 factor, so up to some factor. So if delta E over E is small, then you can write this as 1 minus some constant factor times delta E over E. And you want to get rid of this one. This one makes a problem. So if you want to get rid of this one, then you subtract it from RAA, and then you get really 1 minus RAA is really directly proportional to delta E over E. So what I want to say is that at high momentum and high centralities, 1 minus RAA becomes a direct observable of the energy loss of jets which transverse the medium. Instead of RAA, RAA is not directly proportional, but 1 minus RAA is directly proportional to the fractional energy loss. And that is the reason why we introduce 1 minus RAA. And I think that that is actually much more natural variable than RAA. Basically, we start now using this 1 minus RAA also for comparing it with V2, and then we found that V2 and 1 minus RAA are proportional to each other, and actually they actually carry an information about eccentricity of the system. So that is one of the papers that I actually didn't have time to present here today, but this is, if you're interested, you can read it it is available on the archive. It is very interesting how these two, when you divide these two, you obtain both in the data and in the theoretical predictions, you obtain a flat line, and you actually, this flat line is proportional to the eccentricity of the system, and through this you can extract the eccentricity of the system. So I think in general that I promote that experimentalists should keep the RAA, but should also move when they show RAA to also show 1 minus RAA, because I think that is very important observable, which is directly proportional to the energy loss, direct observable of the energy loss.
Can I ask a quick clarification question on that?
Yes.
So in this formula that you have here with the 1 minus T to the A, L to the B, and then the parentheses, does the term in parentheses multiply that TL term, or is it just another way of writing it?
Can you repeat it again? Sorry.
Sorry, on the previous slide?
This one?
No, on the previous slide.
This one, okay.
Yeah, in the bottom right-hand corner, there's a
yes.
large term in parentheses.
Yes.
Is that meant to multiply the T to the A, L to the B, or is that another way of writing the whole thing?
Yes, so this is 1 minus, this is factor C, which is n minus 2 divided by, it is some part of the energy loss, which depends only on the energy, but then times the n is the steepness of the initial momentum. So it is not that simple, but it is something that depends on the steepness of the initial distribution and also on the initial jet or initial jet energy. Then T is temperature. To the A is a factor if you assume that energy loss is proportional to T to the A, some A factor. Then L is the length, L to the B, so this is the length, this is multiplied, and then you have in the parentheses 1 minus, and this is the number of, A is the number of particles in xenon, the size in xenon divided by size of in lead.
Okay, yeah, and I guess I'm really just asking if is this term, like this term in parentheses, is part of that whole formula, right?
This is yes, it is a part of the whole formula because here you have R xenon divided by R lead. So here you will have 1 minus something. Here you will have 1 minus something. Then if this something is small, you can move it upstairs, and then if you move it upstairs, you get this parenthesis.
Gotcha. Okay, thank you.
Okay. So you can look at this paper. It is very, in this paper you have, this is, you know, really written step by step. So you can really look at it and then you can see what is going on.
So I just wanted to come back to this centrality versus the multiplicity comparison. So why is it more beneficial to compare the xenon and lead RA at the same centrality than at the same multiplicity? Because at the same centrality, don't they then have a different density? I was just trying to make sure I understood that.
Okay, so these arguments here are calculated for assuming the same centrality. So if you have initial momentum distribution, this does not depend on the centrality. But average temperature for each centrality region, we calculated that the average temperature for each centrality region is going to be the same if you move from one system to another system. This is what we calculated, and this is what we predict. And also path length distributions, we also that is what was calculated separately by Pasi and Jussi, and also in a separate study by Jackie Naronha, she also calculated that, and she obtained that these are the same up to rescaling factor a to the 1/3, but only if you compare the same centralities. So you have to compare the same things in two different systems in order to extract the path length dependence. If you don't do the same thing, then these two, 0.2 and 0.3, would not be the same between these two, and then you cannot really extract it. You cannot apply this further analysis if these two are if this relationship is not the same.
So to come back on that, do you mean that so comparing two systems at the same collision energy, they should have the same temperature if we compare the same centrality region?
Same average temperature.
Yes.
Yes, that is what we calculated. The same average temperature, and their path length distributions will be the same, exactly overlapping with each other up to this rescaling factor a to the 1/3.
Okay.
But only if you compare the same centralities. If you compare two different centralities, then these two will not be the same. So then you cannot do all this analysis.
Do you have any hint if this would still be true at lower energy, at weak energy, comparing two very different systems?
No, because we really have, the problem is that we have to, in order to do this, to propose this, we had to assume that delta E over E is small. So that when you have 1 minus delta over E time in the parentheses up to some n factor, that you can write this as 1 minus n times delta E over E.
Mm-hmm.
So you can do this only if delta E over E is small. And in RIC, delta E over E is not small. Delta E over E is maybe 20%, sometimes 30%. So this is not small. So it cannot really cannot be applied. This will not be this will not be really justifiable to do.
Right, that makes sense. Thanks.
Yeah, interestingly, in the same paper, I won't share it again, but there are REAs available at the same centralities as well. They just didn't take the ratio. So if one could do the exercise, it is available actually to do the 1 minus REA.
Yeah, but I would also have to notice that, you know, the error bars are very large, so it is questionable what you are going to obtain. And if the error bars are, you know, if you predict that something should be 0.73 and you obtain 1 plus minus 0.8, then you can get everything. So basically, it's really important that we have high luminosity and low error bars really to extract anything. My honest opinion is that we need more than 1 day of xenon measurements to really try to extract this. We should have high luminosity measurements.
There might be an extended.
Yes. So that is what sometimes I always, you know, at every conference I try to advocate that we should also measure. You know, we have a future in LHC, so we should try to measure small systems. You know, once we finish with light, we should move to smaller systems and try to measure them with the same luminosity as large systems.
Yeah, we might have an extended oxygen run coming up. So
yes, that would be nice. Yes.
Yeah.
Right. So that's actually a lead into a question. If you go to slide 28, oops, my slide numbers are wrong then. Anyway, you show lighter systems, you mention oxygen, but you don't show any calculations. You show asymmetric systems. Do you think that oxygen as compared to xenon will make a difference in the measurements?
So do you think about this slide?
No, I'm talking about a symmetric system, oxygen on oxygen, which is being proposed both at the LHC and at RIC.
So you think about running oxygen, right?
Right.
I just don't understand the question. So
the question is, for such a light system, do you expect to get measurements that will tell you something compared to the asymmetric systems which you have calculated and the xenon lead system?
Okay, I really don't know, but what I think is my answer is no, I don't know, but let me elaborate. So what I think is that this would still be very interesting, because what we would like to do with this proposal is to see whether the quark-gluon plasma exists at small systems or not. So at this point, we know that it exists at large systems, but we don't know whether it exists at small systems. And then in small systems, we only have proton-proton on proton-lead collisions, basically. So if we would have oxygen, this system would be something in between to see whether you have an onset, you know, whether we can do something and whether we can make predictions with quark-gluon plasma in oxygen. So assuming that we really have a quark-gluon plasma in oxygen, I think that we should get, and that you can really calculate in oxygen different centralities, as I assume that you should get something that resembles to this what I have shown here. But it is a question whether that would be possible and whether we really have quark-gluon plasma in such systems or not. I don't know if I answered your question.
Yeah, you did. I guess that also.
But to add this, I also don't think that oxygen is enough. I think that we should add at least argon or krypton, because oxygen is still very small, and we would need something which is in between. So that basically when we go from very large system, which is lead, And then you have xenon-xenon, but xenon-xenon is just 1 day. So basically, it is not that applicable. You know, the error bars are so large that you can really not extract too much. So if you want to have high precision to really see whether you have an onset or offset of core gluon plasma, we would have to need something in the middle, which is relatively large system, but it is still relatively small, something like argon or krypton, and then to have some small systems such as oxygen. And then I think that would be perfect if you would have two of them to compare the results and then to see how your high PT predictions change once you go from very large to very small system, and to see whether you get deviations and whether you get something more than you know, whether you have still core gluon plasma or there is something which is appearing, something new. And I think you need systematics. And in this case, you really jump from very large to very small. And I think we need something in the middle as well. So this is a proposal. If you start to measure, you should add, if possible, some, like somewhat larger system as well.
Okay, that's exactly, you're answering a question that I exactly want to answer. Okay, great. Because I also think that, just one more point, and whether it's going to show you anything could be problematic.
Yes.
And it's always a question of statistics also at the colliders. So
yes, and these are two opposite scenarios. So you have something very large and something very small, and if you have something in the middle, then you have 3 points to compare. So basically, then you can see deviations. In this case, you really have something with the two opposite sides. So I think we should have something. I advocate, like, if possible, to measure also, at least krypton or argon. Maybe krypton would be better because it is larger, but whatever, both of them would be fine.
Thanks. If no one else has a question, I have another, maybe a bigger picture question, at least from my understanding. You say that, the high PT RAA and V2 are sensitive to the thermalization time, in particular the late thermalization time. And, if we look at V2, we understand, or at least we conceptually and intuitively understand the low PTV2 from arguments of, the typical flow arguments and the pressure differences and, the system as it evolves. But now if you go to high PTV2, if you have a difference in the thermalization times, I'm just trying to understand your view, and set it, so I'm soliciting it, of how high PTV2 comes about.
So
it's not just low PT thermalization, the system just expands under pressure difference or something, but what about high PT V2?
So high PT is a pure consequence of the energy loss. So it is simply said, and if you really do it very exactly, it is simply the RAA in in-plane direction minus RAA in out-of-plane direction divided by the average RAA in in-plane plus RAA in out-of-plane. So minus divided by plus. So simply it is difference in RAA in two different directions. And that is simply the differences in the energy loss in two directions. So that is simply it. So the V2 is a consequence of the energy loss for high PT. For low PT is a different thing. And for high PT is a consequence of the energy loss. And that is why I think that this is important, because as I said here, this energy loss will strongly depend on the temperature evolution of the system, so it can measure these differences adequately, and then it is sensitive probe for tomography.
So this high PT, following up from there, there's an Atlas paper, high PT V2 in in P lead, right? Up to 40, 60 GeV, but there have been jets at that measurement, at that PT, and there's no energy loss.
what we would like to do actually is to run all of this with temperature profiles in small systems. And we would be really interested to do this. However, our model 3+1D still cannot run on small systems. And moreover, Pasi Huvinen has a strong opposition that really hydro can be applied to small systems. So this is somewhat of a problem. But on the other hand, if we manage to get a temperature profile from other groups, we are trying to get, but somehow due to Corona, we didn't manage to get the temperature profiles. So if we get the temperature profiles from low PT generated, we would really want to put them in our framework and then see what we get. And then we see what we get for RAA, what we get for V2, and see whether this is consistent with what is seen. And then we can say something about whether what we see, whatever we get, I think it is going to be useful. If we get that it does not agree with the data, then we can say simply, from our perspective, this is not quark gluon plasma. If we get that it agrees with the data or sort of agrees, we can say it can be quark gluon plasma there. So I think that is very important, but we need these temperature profiles, and as soon as we get them, we will apply them, because our DREENA framework should be applicable based on assumptions that we have in our framework. It should be applicable even if we put temperature profiles from small systems, and hopefully we will do this in the future.
And is that the only thing that let's say the DREENA framework needs to change the whole thing to making prediction on small systems? It's only the temperature profile?
It just needs temperature profile, yes. So basically the framework is such that you just put a temperature profile in it and it will give you predictions. And whatever temperature profile, so we are still not at that stage basically, but our goal is also to get temperature profiles from parton transport. These are not really temperature profiles, but they're close to temperature profiles. So basically they can generate sort of temperature profiles, because if they assume that they're close to thermal equilibrium, they can generate temperature profiles. So then they can send us their temperature profiles and we can test them. So whatever temperature profile we get, we can simply put it in and see what we get. So basically what was very interesting and what we saw, and this is our preliminary result, which is still not published, but it is going to be published. We have saw that if you use I think it is Vishnu, but Vishnu, which assumes free streaming of low PT particles before thermalization. And if you use that, then you cannot recover the high PT data. So basically, that kind of scenario simply does not work. So this is something that we obtain. We still need to test it further. But this was very interesting to us that we see a clear difference if you use that, or if you use that you assume absolutely no interactions before thermalization. So it is really interesting thing to see that you have such a discriminatory power with high PT data. On the other hand, low PT data agrees perfectly between each other.
Yeah, I still have another question.
Yes.
About the observable that you propose, about the 1 minus the RAA, you divide two different systems. Mm-hmm. What is your take on if you would calculate the RAA in the same system, but you would select different event properties? And here I'm a little bit hinting at directly trying to probe the path length dependence by using a high and low V2 event, so event shape engineering. Mm-hmm. If you would do that, what do you think? Like, if you would calculate, for example, high PT jet RAA using event shape engineering, and you would then compare just the ratios of the RAA to the 1 minus RAA, do you again gain something in taking the 1 minus?
So can you repeat it? I didn't really understand. Can you repeat again?
Yeah, so it would be interesting to measure the RAA for high and low V2 for events that have a very high and low V2. That will probe a little bit the path length dependence, right? Because it will go in and out of plane. And then would there be an additional advantage if you would go to the 1 minus the REA observable that you propose here?
Yes.
So the fraction that you see on top, it wouldn't be the xenon-xenon, but it would be lead-lead in plane and lead-lead out of plane, or high V2, low V2.
Yes. So as I said, I don't know if I understood you correctly, but as I said, 1 minus REA is direct observable of the energy loss. Under the assumption that the energy loss is small. So, and what we have shown in a separate paper is that 1 minus RAA is proportional to V2. So from that perspective, my honest opinion is that 1 minus RAA has equal advantages as RAA. And for experimentalists, to calculate both, to show both RAA and 1 minus RAA is the same thing. Once you calculate one, you can simply calculate another one. Really, it is not a hassle at all. And then what we see is that 1 minus RAA is such, at this point, we are also studying whether we can extract the dead cone effect by studying dividing 1 minus RAA for two different heavy forks, for example, for charm and bottom. And we see something, but this is still work in progress. So basically, we see that, in our opinion, 1 minus RAA observable is better than RAA, but on the other hand, RAA has also its own advantages. So I think in the future, if possible, the experimentalists should really move over toward using both of them and then comparing both of them.
Yeah.
So you can look at this paper, which is extracting the eccentricity from high PT observables, and you can really see how nicely high PT data, putting aside our predictions, the high PT data for CMS, Atlas, and ALICE put on top of each other. You just use 1 minus RAA, V2 divided by 1 minus RAA. And you get that all of these data are exactly on the top of each other, and they are exactly flatline. And then with Bjorken expansion, we show that this is an initial eccentricity. At this point, we're studying this with full hydro, and we see that this is not an initial eccentricity, but it is going to be an average eccentricity of the system that JET sees. But this is really, this straight line from our model still stands. It still agrees with the data, and you really see that you see something, basically, that really these two are proportional to each other. And that this proportionality follows this eccentricity, though not directly. It is not exactly the same. It follows. So as eccentricity increases, this observable also, this ratio also increases. So it really carries an information about the eccentricity. So that is why I say this 1 minus RAA, in my opinion, is very nice observable to use to study, the properties of Corcoran plasma. Not only for this, but also for other implementations.